Let's take a look at section 2.4, a library of parent functions. In this section, we're going to look at some of the very common algebraic functions we're going to work with here in this course. And those functions are the squaring, square root, cubic, reciprocal function, linear functions. And what we're going to do is look at these parent functions and look at some characteristics of those, such as a domain, range, is it even, odd, or neither, increase, decrease, constant. But we're just looking at these parent functions, and then we'll also look at a piecewise function and graphing some of those. But the key is we need to recognize if you're given a function, what is its picture or its graph going to look like. So very first one you should be familiar with, a parabola. It comes from a quadratic, x squared. When you see a function that has an x squared in it, it is going to be the shape of a parabola. Looks like that. It's centered at 0, 0, and its domain, since I have arrows in both of these upper quadrants, that means it's going to infinity in all these directions. So the domain is negative infinity, whoops, that's a parenthesis, negative infinity to positive infinity. The range starts here at 0 and goes up to positive infinity. And because that's a closed circle, we're going to have a bracket on the 0. Whenever you see an absolute value, you need to know it's going to be V-shaped. It starts here at centered at 0, 0. And we've got our V shape like this, similar to the parabola. It's just a nice sharp curve, nice sharp edge right there. These arrows indicate we're going to infinity in each direction. So the domain is negative infinity to positive infinity, and the range is the same as the previous one, 0 to infinity. Another parent function you need to be able to recognize and graph is the square rooting function. It is this arcing kind of shape, centered at 0, 0, arcs out to the right. Its domain and range would be a little different than the previous because it's just like just this piece of this graph here in quadrant 1. So the domain starts at 0 and goes to infinity. The range starts at 0 and goes to infinity as well. And notice brackets on both of those zeros. Other parent functions you need to be familiar with would be the constant function. That's just a horizontal line. So let me draw a horizontal line here at 4. Those arrows indicate it goes to positive and negative infinity on the left and the right. So that means my domain is negative infinity to positive infinity. And my range is a little bit different here. My range is actually a single value of 4. The only y value that this function uses is the value of 4, or 5, or 7, or whatever the y value happens to be that your graph is running over. If you thought about that in terms of ordered pairs, every one of these ordered pairs would have a y value of 4. And that's the only y value we would use. Need to be familiar with the cube, the cubing shape. Looks like this, kind of this S sort of shape that runs through quadrant 1 and 2, centered at 0, 0. And because of these arrows, I'm going to negative and positive infinity in all directions. So the domain is negative to positive infinity, range negative infinity to positive infinity. We all need to be able to draw lines. We actually did some work with lines, but when there's no exponent or nothing funny being done with the x, we're graphing a line. And again, because of these arrows, the arrow in this quadrant says I'm going to infinities. The arrow in this quadrant says I'm going to negative infinities. So the domain and range are the same as the previous one. Let's see, did I have another one here? Oh, we've got one more, the reciprocal function. That's when we see this fraction with the x in the denominator. So this is a basic parent function. 1 over x is going to have this as its graph. It's kind of interesting. It's sort of two curves. One in this quadrant and one in this quadrant. But notice how these curves are actually going to not cross the x or y axis. It's just going to ride right beside it. It'll never cross either of those axes. So for that, I can't ever have x equals 0. So x cannot equal 0. So for my domain, I need to exclude that value. So I would have negative infinity to 0 with a parenthesis, because I need to exclude the 0, pick back up at 0, and go to infinity. Those two parentheses on the 0 tell me that I'm excluding the 0. The range would be the same way. Y can't be 0 either. So negative infinity to 0, 0 to infinity, that's our notation for saying, that's an interval notation for saying let's exclude the value of 0. So again, when you see x squared, your brain needs to think parabola. When you see, what's our next one? When you see an absolute value, your brain says V-shape. Square root, your brain says we're arcing out to the right. Constant function is a horizontal line. X cubed is this kind of weird curvy S shape. That's what you have to have in your brain. And a line, when there's nothing done to the x, we're just graphing a line. And finally, reciprocal has these two curves in quadrant 1 and quadrant 2. Okay, let's look at graphing a piecewise function. So let's look at this function defined by two pieces. So actually what we're going to be doing is drawing two separate graphs. The first graph we're going to draw is this one, which is a line. We'll draw that graph, but that graph will stop at 3. That value of 3 is my transitional value. Then I'll pick up after the 3 and draw this line. So let's look at an example. This will help you as we go through this example. So please notice that the domain is split into two intervals, one that's less than or equal to 3 and one that's greater than 3. I'm going to draw two graphs. This guy right here, I'm going to draw to the left of 3. And the second graph, I'm going to draw to the right of 3. 3 is my transitional value because that's the point where the graph makes its transition from one type to another. So let's see what happens graphically at this transitional value. That's really important to get that part right. So we're going to work on some ordered pairs. So let's split the 2. Let's split that up into two equations, and let's just plot some ordered pairs. So if I put a -1 in place for x, I get -1 plus 2, which is going to be what? 1. If I plug a 0 in for x, 0 plus 2 is 2, a 1 in for x, 1 plus 2 is 3, a 2 in for x, 2 plus 2 is 4, and a 3 in for x, 3 plus 2 is 5. So created all those values. Simple enough. Let's plug in some values for the next one. So I've got a list of values, and actually I want you to realize that I have 2 right here, but I cannot use 2 in that equation. I can only use values that are greater than 3. So 2 has no bearing. I'm going to plug in 3, and we're going to talk about that, talk about what happens. So if I plug in a 3, I'll end up with a -3. If I plug in a 4 for x, I get a -4, a 5 for x, a negative 5, a 6 for x, a negative 6. Here is where we need to make a decision. Somebody's going to get an open circle, somebody's going to get a closed circle. That's what we need to figure out. Who gets what? So this transitional value and this transitional value. I evaluated both of them at 3, but only one of these graphs can actually have that as a point. And because this part has the equal to, when I graph this point 3, 5, it is going to be a closed circle because that means it's included, a dot. Because this one does not have the equal to part, then when I go to graph that function on that side, this transitional value of 3, negative 3 is going to be an open circle because this one did not have the equal to, so I can't include it as part of my graph. The 3, 5 is going to be a closed circle. So let's see how we're going to graph that. So we're just going to plot some ordered pairs. So I've written down the ordered pairs from above, and let's plot those. So the first function that I have here, I have his ordered pairs here, and let's plot it. So negative 1, 1, 0, 2, 1, 3, 2, 4, and 3, 5, and that's a closed circle. Now I'm going to connect those dots. But notice I am not going to go any further than the 3. That's where it makes its transition to the other graph. So now on the other side of 3, I'm going to graph my next one. So the next graph gives me the ordered pair of 3, negative 3. So 3, negative 3 is down here, but it's open. Then I've got the point 4, negative 4. 5, negative 5, 6, negative 6. So this graph is going to continue in that direction. Notice I didn't continue it to the left because to the left of 3 is this side. To the right of the value of 3 is this equation. So right there, 3 is your transitional point. And I've got to figure out what happens at 3, and we figured it out because we knew closed circle there, open circle here. This graph would pass the vertical line test. I can't have 2 closed circles here and here because a vertical line would intersect at 2 points. So that's why we got to have one closed and one open. I'll stop this video here and do another video to finish this note sheet with the applications.